Okay, perfect. Welcome everyone. Thank you very much for coming today. I know it's been a long week. Today I'm going to sort of give you an overview of Anoma. And Anoma really is the first generalized intent-centric architecture. And what are intents? So just very briefly to begin with. Intents are the most fundamental unit that we have in blockchains, effectively. So currently we always live in this transaction-centric world, but transactions are sort of a lie that we tell ourselves are the most fundamental thing, because it comes from Bitcoin, right? Like with Bitcoin, you had a transaction-centric model, and Ethereum made this transaction-centric model in Bitcoin programmable. The problem is when you look at a lot of the DeFi applications, for example, users don't have transactions, they have intents. As in they have partial state transitions. I want to, for example, buy some ETH for some Bitcoin. That's not something I can execute on chain. And so I can express it as an intent, and then have decentralized counterparty discovery and distributed solving done to it. And so far, really, no one has generalized this approach. Everyone is kind of starting to think on like an application-specific intent level, but Anoma is the first intent-centric architecture for generalized intents. Because intents represent the unit of compute, whether this is a rollup, a DEX protocol, or even like a ZK rollup. It's always intents under the hood. So let me go a little bit into the evolution of protocols and sort of how we got to today, and what previous trade-offs we've made. So really the first generation of protocol is Bitcoin and Bitcoin-like systems. And they are distinguishing themselves by being scriptable settlement, as in you don't have a full programming environment, you have some limited scripting capabilities. And sort of in this category is also things like Zcash, Monero, Dash, Litecoin. This is sort of the early versions of purely transaction-centric models that were designed so that I could go to a store and buy some milk in exchange for some Bitcoin. Given the limited scripting capabilities, we could still build other interesting things like colored coins and Namecoin, but they were always incredibly clunky because pretty much you had to fork Bitcoin Core in order to make something like Namecoin work in practice. And then we moved into sort of, with Ethereum in 2015, we got programmable settlement. We took this idea of a transaction-centric world and tried to make them fully programmable, because it allowed us to do very interesting things like moving colored coins into ERC20s, Namecoin became ENS, but we also got a bunch of new things like DAOs and new kinds of assets, NFTs. Yep. So let's quickly go into sort of the state where we're currently at. We're currently in this programmable settlement plus world. And this is to say that really since Ethereum in 2015, the fundamental architecture hasn't changed. They're always sort of, it's Ethereum in a slightly different color and at a slightly different speed. But like, there's not much architectural distinction between something like Near, Solana, Ethereum, Avalanche, or Tezos. They are very much fundamentally the same thing. Albeit some of them have made advances in symbol resistance, we got advances in scaling, we got advances in consensus mechanisms, but they're fundamentally, it's the same sequentially executed VM model as was introduced by Ethereum. And then maybe sort of, since we're also talking about interoperability here, like Cosmos and Polkadot were sort of very orthogonal developments. Like they just came up with Cosmos came up with a very interesting new consensus that allowed us to have communication between two separate blockchain instances. So where is it heading? And by the way, I can guarantee you, intents are coming whether you like it or not. The next generation of blockchains is all going to be built around this idea of intents. In very much the same fashion that sort of after Ethereum, all the other major blockchains that came along, they were all based around the same basic fundamental architectural principle of being a VM-centric or transaction-centric world. Yes, so Anoma is really the first specification for a generalized intent-centric architecture. And this is hard. Like, we sort of like spent the last 2 years thinking about, from first principles, how do we actually architect these systems so that they can truly scale to a global audience. And today I'll quickly go into what this actually means in practice. So what is Anoma? Anoma is the first ever intent-centric architecture and introduces a new paradigm for building infrastructure layers. It is designed for applications that involve infinite users using infinite number of intents, each of arbitrary complexity. And here, maybe it's important to also mention that, like, An intent is just some state plus some code. It is a very simple yet a very powerful concept. So you can build things like rollups on top of this. You can also build things like dexes on top of this, but in fully decentralized fashions. So with an intent, a user expresses what they want, not how to get it. Generally speaking, when you think of how a Ethereum transaction gets executed, it's a user specifies some execution trace that the transaction takes through the EVM. The user does not specify a specific state change that they care about. This is massively problematic if you want to do decentralized counterparty discovery and distributed solving, because how you interleave these execution traces matters to the final state outcomes, right? Like, if I have a transaction, if I have some existing EVM transaction and someone else has an existing EVM transaction, it matters which one gets applied first, because they may operate on the same state. With intents, they are just state updates. So like, you specify exactly what kind of future state you're willing to take. And then the system can figure out around this how to best structure itself in order to fulfill this intent. You do not have to describe exactly how to get what you want. The system can figure this out on your behalf. So for example, you can say things like, I want to trade 1 Bitcoin against some ETH, against, let's say, 100 ETH. And as a result of expressing the state preference, you don't care whether there's 1 counterparty, 100 counterparties, there's a bunch of Brink trades in the background. So intents are binding programmatic commitments to state preferences. And this leads to a very nice declarative paradigm for dApps. So this is sort of a super simple example where a user just submits a specific intent that is a specific state preference that they have for the future. And then the system, the protocol can figure out, or the protocol allows structures to emerge where solvers can figure out how to correctly settle these things. And then in the end, a user only has to check whether it was settled or not. And of course, if you're trying to create intents that are unsettable because there's maybe no counterparty in the world that's willing to sort of trade with you, then those intents wouldn't end up being settled. One of the best parts, though, is that this also leads to much better privacy guarantees. This is sort of a generalized architecture, but it maps much better into this world of privacy-preserving compute. And the really fundamental thing to realize about privacy-preserving compute is that the state model changes, right? Like, in the existing world, we always have this model of, like, there's a large part of global state that we all read and write to. This really doesn't work for privacy-preserving compute, because in that world, the state gets pushed to the edge devices. So you need to have some capability to be able to communicate proofs over your local edge state and have computation done over your local proofs that can combine your local proof with other people's local proof. Intents are very flexible, and as a result, you get user-defined privacy. This is not in the traditional world, really, the model is always it's an application choice whether something is private or not, right? Like, you have the private DEX and you have the transparent DEX, and they're fundamentally different in terms of how you interact with them. And this is like a choice that the developer of that DEX made. With intents, the choice becomes a user choice, where a user can decide whether, if they attach a zero-knowledge proof to their intent, then they're interacting with the DEX privately. If they attach a plain text signature to the intent, then they're interacting on the same application but transparently. So privacy becomes a user choice, not an application choice. And so, for example, here you could say things like, I want to trade some Bitcoin against ETH, but I don't attach a plain text signature. I attach a zero-knowledge proof that authorizes this. The state is still public in order to allow a counterparty discovery to happen, but the identity of who actually is trading is private. And this is a very flexible system, so once we get fully homomorphic encryption working in a faster fashion, let's say it this way, you can even keep things like the state private, where you reveal really almost no data about what you're doing on these systems. And again, I keep talking a lot about the example of trading. This is just because it's easy to understand. This generalizes to arbitrary state updates. This is why this generalizes also to rollups, for example, because in a rollup, let's say everyone here in the room wants to get together into one rollup. We just issue the intents. I want to transition from some state A to some state B. The next person wants to go from B to C. The next person wants to go from C to D. At some point, we say, well, this is enough to justify the rollup compute, and then the solver takes all these intents, does one compute, for example, like a zero knowledge proof over the state updates, and then this is settleable on chain. Right. This is the entire overview of Anoma's architecture. And I'll sort of go from left to right through what the individual components actually mean. So on the left, you have the user, and users have choices. Users can make a choice whether they want to issue a transparent intent, a shielded intent, or private intent. And this sort of breaks down to the categories of what kind of level of cryptography users want to be using. Transparent intents are just plain text signatures. Shielded intents use zero knowledge proofs, and private intents will eventually use fully homomorphic encryption. Users submit this to the intent gossip network. And the intent gossip network is not consensus critical. So it's a sparse global network of intent gossip nodes where different intent gossip nodes can make different choices on what kind of intents they want to receive. For example, my node could make a choice that I want to receive all intents. Your node could make a choice that you want to only receive the fungible token intents. Some other nodes could make a choice that they only want to receive the OpenSea intents, right? So different intent gossip nodes can make different choices, and we don't have to have a global view of all the intents. This also gives you local scalability, by the way, because one of the fundamentally limiting factors for consensus is sort of speed of light communication, and if people locally want to trade, the most latency optimal version is not to go to a global consensus system, but to have a local consensus provider that, for example, just provides sequencing or ordering services for everyone in Seoul, right? And so this structure, the important thing is the architecture doesn't fix the topology of the network. The topology of the network can follow from the actual patterns of user behavior. Yes, so then you have solvers. Solvers look at a number of intents, and again, they can make local trade-offs. Maybe some solvers only do fungible tokens, some do NFTs, some do roll-ups, some do like Gitcoin multi-sigs. This is also an intent-centric system. And when they find intents that match with each other, that are solvable, they put those together into a transaction. Sort of a trivial example is, I want to do A for B, someone else wants to do B for C, third person wants to do C for A. Solvers finds this, puts this into a transaction, and then submits this to the actual consensus provider. And here Anoma has an encrypted mempool using Fairview, or Fairview's threshold cryptography, because front running is really not it's not a given design in these systems. It's actually very easily solvable once you start architecting these systems from first principle. So with Fairview, all transactions are encrypted against the public key of Fairview. Then validators sort encrypted transactions into blocks. Now the ordering of the transactions is fixed. On the next block, the validators jointly decrypt all these transactions. The ordering has been fixed on the previous block, so they can't inject or reorder them. And then they just execute the decrypted transactions. And then what does this execution actually look like? Well, this uses Tiger, and I'll speak a little bit more about Tiger in a bit, but Tiger is the unified execution environment of Anoma, and it's one large ZK circuit. It's Tiger is a ZK circuit based on Halo 2 as a proof system that allows you to do recursive verification. So for example, a solver that takes in some shielded intents would compute a recursive proof over those intents, and then submit that transaction with its associated proof on chain, where Tiger would handle the execution. One of the super nice benefits of this is that we can have a unified environment between transparent, shielded, and private intents. So yeah, this is Tiger, the unified execution environment of Anoma. Actually, how am I doing in time? Okay, perfect. Then there's also Typhon. I've been speaking a lot about sort of consensus providers and local versus global ordering. This is really implemented by Typhon. It is a combination of the heterogeneous narwhal for the mempool, as well as the heterogeneous Paxos papers for the consensus part. If you're familiar with Tendermint, Typhon is like Tendermint in the normal case, but in the best case, it can provide you on-demand sharding. That if two systems have a large enough overlap in their validator set, they can decide to opt into a sharded ecosystem, let's say 1 hour every month, in order to have synchronous state updates between those two systems. And this is actually really important because this is what gets you true global scale, because you don't have to have one globally scalable single consensus model, but rather people can make local trade-offs on like what is security to them, because like my parents will want like localized security in Germany. They don't, like they trust the local government more than they trust Ethereum validators, right? And so different people are allowed to make different trade-offs here, but you still get composability across the system. For example, with Typhon, you could say things like, if I want to do a large block trade across New York and London, maybe the fees are high enough to justify paying for the cost of having a sharded system for 1 hour between New York and London. Then you also have Vampire, which is, I've been speaking a lot about circuits, and Vampire is really the LLVM for polynomial circuits. If you know what LLVM is, that may make sense to you. At a very high level, LLVM is an intermediate representation that compilers use so that not every high-level programming language has to build its own backend in terms of targeting different chip architectures. And so with Vampire, you can just describe a circuit in the Vampire language. For now, you can do this directly. In the future, expect higher-level languages to target Vampire directly so that individuals don't have to write Vampire. And then it's a compiler flag, whether you want to target Halo 2 or Starks or FHE or PlonkUp. Currently, Halo 2 and PlonkUp is supported, but there's sort of experimental work on building a Stark backend as well. And the best component part is that if someone later on adds an extra optimization or an extra backend, you don't have to rewrite your program. Like, you can just write your circuits once and then at some point later decide which proof system you want to target, which is very different than what's happening right now, where languages are tied to specific proof systems. Then you also have Juvix, which is the first high-level language where developers don't have to think about what a field element is anymore, which targets Vampire. So with Juvix, you can write normal-looking programs that end up being turned into circuits by a sensible compiler stack, without having to know what a field element is when you write the program. So what can you build with Anoma? You can build a bunch of known dApps, but fully decentralized. And here it's very important to understand because most people don't realize this. Pretty much all major dApps you have nowadays are centralized. Like when you interact with OpenSea, you're sending a bunch of signed messages to a server running on AWS in California. When you interact with your favorite rollup, you're also sending some signed message to a rollup sequencer that's run by a central entity. So you can get rid of all these centralized counterparty discovery and solving components using Anoma. So you can build things like decentralized optimistic or ZK rollups, DEXs like DYDX or 0x, NFT marketplaces, even things like Gitcoin quadratic funding and Gnosis Safe are good examples of why we need intents. Because what actually happens in a Gnosis Safe multisig is that individual users sign their part of the multisig. Then this gets sent to the Gnosis Safe server, and the last person in the chain pulls all the signed messages from the Gnosis Safe server and submits them on chain and pays for the transaction. But you can also build a bunch of novel things, like runtime rollups. So once you have an generalized intent-centric system, rollups just are free. And you can have partial rollups, because if I have some state, some intent that goes from A to B, and someone else has an intent that goes from B to C, any solver in the network can take these two intents and create a partial solve that goes from A to C, and if a day later C to A comes along as an intent, then the next solver in the queue, or the next solver in the network that sees this, can submit this as a fully fledged transaction on chain. Anoma used to be described as a multi-party, multivariate bartering system. If you've seen a bunch of the early talks, this is how we used to describe it. But it's effectively the idea that intents create user-defined order books, but over arbitrary state updates. You can, using Fairview, you can also build DeFi dApps such as sealed bid second price auctions. You can build privacy-preserving NFT marketplaces, things that are really impossible to be built right now. And this is actually a actual example of CowSwap, but in a fully decentralized fashion. Users submit intents get encrypted against Fairview. The application can define a batching or like a batch length. So the application can say, well, my batch length is 10 blocks. During those 10 blocks, all the intents are just stored on chain in an encrypted fashion. After those 10 blocks, the validators will then decrypt those intents. And then, let's say, again, this is application defined, but then solvers have the chance to, maybe for 5 more blocks, create solutions that are submitted on chain. And on chain, they're actually then verified against some optimality function that the application can implement. So you can build things like fair price or uniform clearing prices like CowSwap, but you can also write arbitrary optimality functions, so you can optimize for whatever you care about. Yes, so on the novel dApp part, like when Ethereum came out in 2015, we really didn't know what was going to happen. We sort of like said, well, this is very novel in terms of what are the possibilities, but they couldn't tell you like these were the specific applications that are going to be built. And it's kind of the same with Anoma. This opens up a totally new can of worms of the kinds of applications that are possible to be built. Right, very quickly on deployment models. Anoma is an architecture. This is, it's an architecture that you can deploy into many different places. You can decide to deploy this as an L1, for example, like a sovereign chain or even a local chain where the city of Seoul can decide to take Anoma as an architecture and just run a local proof of authority chain. You can deploy this as an L1.5 in order to decentralize a specific application, or you can even deploy this as an L2 to, let's say, places like Ethereum. Again, this works because all of Tiger is just one large ZK circuit, so you can create a ZK rollup there for Anoma. And this is really fundamental here, that like different users will have different security models or requirements for the security model. Like people in Argentina may want Ethereum security, right? Like, and they can make this choice themselves. But it's very hard to make an argument that like there's a one best security model across the globe. This is sort of like saying the one chain to rule them all thesis or the one security model to rule them all thesis. It's kind of like saying we should have a one world government that everyone checkpoints into. And this just seems very unlikely to actually work in practice. Because even if that system is decentralized, you still have a centralized failure component that you're fundamentally trusting. So a much more stable system is where you can have many different independent security models that can interoperate freely with each other. So yeah, Anoma is founded by myself, Awa, and Chris, and is being built by the first core dev team at Heliax. There's a bunch of cool swag in the back if you like it. Yeah, thank you very much.